In this video, I'm going to continue to go over section 2.3. So last time, just to recap, the last time we learned the Newton's method, right? So it's really powerful, and then the sequence of the approximation converts to the exact solution really fast, and then but there is the drawback was the is that we have to figure out the derivative of function f of x, right? So to overcome the drawback, we have to we're gonna apply the slope of the secant. It means that we're gonna approximate the slope of tangent line, which is the f derivative, as the slope of secant line, which means that we use definition of the derivative to uh, approximate f prime instead of the finding f prime. Okay, so to see, you can see that to overcome the major weakness in Newton's method, we introduce a slight the variation. See, f prime p n minus 1 is limit f of x minus f of p n minus 1 over x minus p n minus 1, and x approaches p n minus 1. This is just definition of the derivative f at x equals p n minus 1, right? So now first we let x equals p n minus 2, and then to find the p n minus p so the goal is to find out pn. So in Newton's method, right there, give me a second. Was Yeah, so pn equals pn minus 1 minus, oh, not here. So remember, I'm sure that you know that. Yeah, so pn is equal to pn minus 1 minus f of pn minus 1 over f prime pn minus 1. We see that here, f prime. So we're going to replace f prime with the derivative of the f prime without applying the limit. Okay, so right there. So now f prime pn minus 1 can be approximated as like this: f of pn minus 2 minus f of pn minus 1 over pn minus 2 minus pn minus 1. So this is just actually what slope of the secant line passing through the point, 2 points, pn minus 2 comma f of pn minus 2, and then pn minus 1 comma f of pn minus 1. So then you may say that, okay, well, I mean, see, we can use the slope of the secant line passing through pn minus 1 comma f pn minus 1 and f of pn comma f of pn. But keep in mind is uh we don't know the pn yet. Okay, we didn't the figure out pn yet. So we have to use the known information, what we got. Okay, that's the pn minus 1, pn minus 2. Okay, so now then, and then we just rewrite that fraction is like this. It's not a big deal, right? So now then we plug in this one into the bottom of the Newton's formula. Okay, Newton's formula in the bottom f prime, we replace it by that fraction and then simplify, then you're gonna get this. Okay, so now then the key minus here, n minus 2 is involved, so n must be greater than or equals 2. It means that you need two initial approximations. Okay, so the technique is called the secant method, and so now then the meaning of this one is the what actually rewriting that the formula secant formula is like this. So first one, we move the pn minus 1 to the left hand side, and then the interchange left hand side, right hand side. Okay, and then the isolate f pn minus 1, you're gonna get this. Okay, so now you see that this is slope. I mean, that is what actually the slope intercept form, right? Sorry, point slope form, right? So, now this one is point slope form in the of the straight the linear equation. Okay, so that's the slope. Okay, and then so now pn minus 1 gonna the given x point. This is given y y value, x value, y value, and then Pn minus 1 going to be what? The x coordinate of the point Pn comma 0. So now you see that the Pn must be a root, right? Okay. So now, okay, let's see. And then, yeah, I told you Pn is the x coordinate corresponding to the y coordinate 0. Okay. So starting from P1, P2 is given, we're going to find out what? The secant line passing through P2 and P1. Okay. Right. We find out the secant line, and then P0 and P1, I'm sorry, given P0 and P1, we're going to find the secant line passing through P0 and P1. And then we're going to find out why the the y x coordinate of the x-intercept of that secant line. So right there, Pn is what? X coordinate of corresponding to y coordinate 0. So it means that Pn is, I'm sorry, not root. Yeah, I made a mistake. Sorry. Pn must be what? X coordinate of x-intercept of that secant line. So P2 must be what? X coordinate of x-intercept of the what? Secant line. Okay. So now, and then what? And then what we're gonna using the P, we're gonna evaluate the function f at x is P2. Okay. So now we're gonna get, so maybe right here, maybe in that point right there. Okay. Let's say this graph is of f of x like this. Right? Then we're gonna find our secant line passed through P1 and P2, which is this. Okay, right there. So now then we're gonna find out what? The x coordinate of the x-intercept of that secant line. Okay, maybe right here, right? So we're gonna find, this is the x-intercept. So we're gonna find the x coordinate of x-intercept. Okay, this is a P3. Okay, and then we evaluate function f at evaluate function f at P3 right there, right? Okay. So now we're gonna find a secant line passing through P2 and P3, which is this. Okay. And now then what? Now we're gonna find out. Then we're gonna find out what? The x coordinate of that secant line, and the x coordinate, that x coordinate of this x-intercept must be what? P3, P4, right? This P4, P4. Okay, and then we find out what? The secant line passing through P3 and P4. Okay, so keep doing that. You see that the x coordinate approaching what? The exact root, right? So that's the how that secant method work. Okay, so now algorithm of the secant method is really similar to the algorithm of the Newton's method, but we're gonna find out what? I mean, the Newton's formula will be replaced by secant formula. You see that here? Okay, so excuse me. So now, right? Okay, so now like this is here. Okay, so and then the P0, P1 must be given. Okay, as an input. All right, and then we're gonna evaluate function f at those initial approximation, saying Q0, Q1. Okay, and then n sub 0 and that must be the maximum number of iterations. Okay, so now and then we evaluate p. Actually, that p means actual p3, right? In the first iteration, we find a p3, right? So this is the formula right there. And then we measure the error, absolute error. So p3 minus p1, p2. I'm sorry, this is p2, right? So we start from p0. I'm sorry. So now p2 minus p1, we measure the absolute error between p1 and p2, and if that absolute error is less than tolerance, okay, then we output p. Otherwise, and then stop, and otherwise we keep going. Okay, so okay, so now then, well, first we find out p2. Okay, then P0 will be updated by P1, and then P1 updated by P2, and then Q0 updated by Q1, and then Q1 updated by what? F of P. Here in the first iteration, P means P2. Okay. So now, here's a note. Newton's method or secant method is often used to refine an answer obtained by another technique, such as the bisection method, since these methods require a good first approximation, but generally give rapid convergence. Yeah, so the Newton's method, secant method generally give rapid convergence. So, but the both method, even though the secant method overcome the was one of the drawback, the Newton's method requiring required to find out the derivative, both methods still has the cons, which is the what they both method require the good approximation. So we first sometimes we're gonna use bisection method to find out the good approximation and then use that solution as initial approximation in Newton's method or secant method. Okay. So now let's see example 2 in the textbook. So find the solution to x equals cosine x. So functional iteration, iteration, a fixed iteration method. Okay. So using this one. So the Newton's method, secant method, we run three methods to figure out to compare those three methods. So you can see that the Newton's method only reach the solution, approximate solution, just 4 iterations. But other secant methods require 5 iterations, and the function iteration method requires 7 number of iterations. Okay, so the convergence of secant method is much faster the function iteration, but slightly slower than Newton's method. Okay, so now each successive pair of approximation bisection method brackets a root p of the equation. That means for each n, the exact solution belong to a sub n comma b sub n. So here in this note, second note, what we want to talking about is this. The Newton's method, and then I mean in the bisection method here, the root p is always is belong to always for any n, the p belong to the what the interval, closed interval a and b, and it's called the nested or the bracket. So that implies that for each n, the bisection method iteration satisfy this one p n minus p. This is absolute error, right? Absolute error. This is bounded by half of the a n minus b n. So this is really I mean, so it's easy to calculate the absolute error, right? I mean, we can easily figure out the how many number iterations required to um, get approximation within certain error. So that which provide an easily calculated error bound for the approximation. So root bracketing, yeah, that kind of property is called root bracketing. Okay. So root bracketing is not guaranteed for either Newton's method or secant. Yeah, so Newton's method or secant, yeah, this is powerful. But so in an analysis, I mean error estimate, in a view of error estimate, Newton's method or secant method doesn't guarantee the doesn't guarantee the root bracketing. So it's hard to do error estimate. Okay. So now in the also you see that Newton's method is f prime is involved. So that you know that's kind of challenge to figure out the error estimate. Okay, I mean the upper bound of the you see that upper bound of the absolute error. Okay, secant method too. Okay, so now to here's the question here. I want to just is there any way to design the method which is same performance as Newton's method or secant Newton's method, but we can easily calculate the error bound like a bisection method? It means that we wanna design new algorithm that has the what the advantage for each method, bisection method, Newton's method, and secant method too. Okay, so now that's the method of force position. Okay, so methods generate approximation in the same manner as the secant method. Why do we have to use that secant method instead of Newton's method? I told you I don't want to figure. I don't want to find out the f prime. Okay, I know f prime in this. In the examples and some kind of toy problems, it's easy to find the f prime, but in real world, it's really expensive to figure out f prime. So we want to avoid finding f prime in the algorithm. So we use a secant method, same manner as secant method, but it include the test to ensure that the root is always bracketed between successive iterations. Okay. So now here, first one, choose the here's the algorithm. Okay. So choosing initial approximation P0 and P1 with P0 times P1 is less than 0. Okay, so we can use what? Intermediate value theorems, right? So big assumption in the bisection method was what? The always two consecutive sequence should satisfy the assumption intermediate value theorem, okay, which is P0 times P1 is less than 0. So choose P2 in the same manner as in the secant method. Okay, check the sign of P2 times P1. Okay, so if P2 times P1 is less than 0, okay, that means what? By the intermediate value theorems, P1 and P2 the clause in the P1 to the P2 must contain the root. Okay, here's the yeah, and then we choose P3 as the x-intercept of the line joining P1. Yeah, that's what we have. That's the how to find our next sequence in the secant method, right? And then here's the other case. What if f of P2 times F1 is greater than 0? Okay, then we choose P3 as the x-intercept of the line joining P0, f of P0 and the P2, f of P2. What does that mean? So then f of P2 times F1 is greater than 0. It means that what? The f of P2 and f of P2, their signs are equal, right? Plus, plus, or minus, minus, right? Okay. So let's say, for example, let's say f of P2 is plus and the f sign of f of P2 is plus. F of P1 is also plus. Okay. It means that f of P0 must be minus, right? Because you see that here, there is what we choose. We did choose initial approximation P0 and P1 with f of P0 times f P1 is less than 0. It means that sign of f of P0 is different from the sign of f P1. If f of P1 is a plus, f of P0 must be minus. F of P0 plus, f of P1 must be minus. Okay, so if what f of P1 is a positive, then f of P0 negative. But f of P2 must be negative, positive, right? Because the f of P1 positive, then f of P2 must be positive. So see that the f of P0 negative and the f of P2 positive is confused, right? So let's see. We assume that let's say this is a positive, then that must be positive, right? But we did choose the approximation P0, P1, so that f of P0 times f of P1 is a negative, means that their signs are opposite. So this is negative, and this is positive. Okay. So now then what? Instead of finding the x-intercept of the secant line passing through f of P1 comma f of P1 and P2 comma f of P2, we're gonna find out the slope of the secant line passing through P0 comma f of P0 and the P2 comma f of P2. Okay, then the exact solution, I mean root, still in the in the closed interval P0 comma P2, right? Okay. So now then we're gonna see P0 right there. We're gonna interchange the indices P0 and P1. Okay. So now the now P0 gonna be P1. Okay. Now P0 gonna be P1. All right. And then check the sign of apple P3 times apple P2. Yes. Let me see. keep doing that. So now the see, so now once we got P3 right there, okay, P3 we find out P3, and then we check the apple P3 times P2. If this is positive, now you see. Okay, then we have two cases, right? Case one, what? Apple P2, apple P3 times apple P2 is greater than 0. I'm sorry, less than 0. Okay, that's good. We're gonna find a slope secant line passing through P2, comma apple P2, and P3, comma apple P3. Second case, if the what if apple P3 times apple P2 is greater than 0? Then apple P, we're gonna find a slope secant line. Okay. So slope secant line, what? Passing through the P1, comma apple P1 and P3, comma apple P3. Okay, that's gonna be P4. Okay, so let's see. Then what happened here? So now let's see. I know it's maybe it's you didn't understand that. So let's see. Let me explain about. Let me explain the algorithm of the method of first position with a figure. Okay, let's say here. Let's say this is the. Let me see. Let's say that's the graph of the. This is a graph of f of x. Okay, right there. See. Okay. So now then, starting from the P0 right there and P1, because we're gonna use we're gonna apply the secant method. Okay. So we're gonna find our secant line passing through P0, comma f of P0, and then P1, comma f of P1. Give me a second. Okay, so right there. And then what? So as you can see, the apple P0 is negative, and then apple P1 is positive, right? And then let's see, apple P2 is negative. Okay. And then apple P1 is positive. All right, that's good. So we can use intermediate value theorem, right? Okay. So what's the P2? P2 is what? The secant x-intercept, x-coordinate of x-intercept of that secant line, okay? And then we have to check the sign of, check the sign of what? F of P2 and F of P1. So F of P2 times F P1 is negative. It means that there are signs in the opposite. Okay, then we apply the secant method. Okay, we just continue to apply the secant method. So that's the, let me use other color. Okay, so that's the secant line. Okay, now then, so now you see that here, the what x coordinate of the x-intercept, P3. By the way, so now then, we still got P2 right there. Okay, so now here. Okay, so now we're gonna the P3. So you see, and then for P3 is we're gonna find out P3, which is the x coordinate of that secant line. Okay, and then apple P3 is just that negative, right? Apple P1, not apple P2. Okay, so now see apple P2, apple P3, both are negative, right? Then we're not going to use the apple P2. Okay, we drop the P2, and then we're going to use P1. Okay, because apple P1 is positive, and the apple P3 is a negative. Yeah, so we use the see, we're going to draw the secant line passing through P3, comma apple P3, and the P1, comma apple P1. Okay, and then now we see now. Okay, so what does that mean here? So give me a second. So now the here when you find out the green, secant, the green lines, which is secant line passing through P3, f of P3 and the P1, f of P1. So in the coding, when you write coding, so now P1 becomes actually P2 when you compute P4. Okay, because the P2 apple P2 times apple P3 is positive because both their signs are equal, I mean, as a negative, right? So we drop the P2 and then we're gonna change the P1 to P2. Okay, and then we're gonna calculate the secant line passing through the P2 apple P2. Now here P2 doesn't mean this one, okay, that one, and P3 P3, and then we got this. And then see, apple P3, apple P4, their signs are negative, right? Same. Oh, okay, then we abandon what? P3. And then now P1 becomes P3 when you calculate what? P5. So this one. Let me see. I think this one. Okay, give me a second. Let's see. Okay, that one. So P5 maybe right here. Okay, should be right here. Okay, P5 here. So now, okay, so algorithm of the method of first position is right here. So starting from this, P0, f of P0 times F must be negative. Okay, you have to choose the P0, P1, that initial approximation, P0, P1, satisfying this, okay? So now you have check. What if, the P0 times P1 is a positive? Then your code, you have to design, your algorithm, your code to return error, return the warning sign or error when what fp0 times fp1 is positive. Okay, so input is a p0 p1 tolerance and the maximum number of iterations, and the output must be p or message failure. But the I suggest you your code return not just a finer approximation, but just sequence of the solution. Okay, sequence of the solutions, and then yeah. Okay, so that's the. Give me a second. Yeah, so from step 1 and step 2, step 3 and 4 is pretty much same as the the algorithm in secant method. Okay, you see that here. This is the what the secant formula, right? Okay, so now then here's things. This is step 6. Okay, and step 5 right there. So we're gonna evaluate FOP. Okay, in the first iteration, that's the actually P2, right? P2. Wait a second. That's actually P2 in the first iteration when I equals 1. Okay. In step 3, we calculate P2. So P2 minus P1 is less than tolerance. Okay. Output P2. If P2 minus P1 is less than 0, that's than tolerance. Okay. And then now, so and then Q equals F of P2. So now Q means what? F of P2. Okay. So F of P2 Q means F of P2. F of P2 minus Q1. Q1 is F of P1 less than 0. Okay, that's good. Then we can use intermediate value theorem to find out P3, right? Okay, all right. So now then P0 gonna be P1 and then Q0 gonna be Q1. So now P0, yeah, okay. So Q0, what's a Q1? Q1 is what? F of P1, okay? So now then yeah, we just simply just update P0 Q0 to P1 Q1. But let's see now. Let's see, give me a second. Okay, all right. But what if Q times Q1 is greater than 0? We don't update the P0, Q0. We only update the P1, Q1. Okay, so that's that's the difference between the secant method and then the method of first position. So Q times Q, which is Q is what, f of P2, right? So f of P2 times f of P1 is greater than 0. That means their signs are equal. Okay, so then we don't use P2 and f of P2. Okay, instead of the P0 and Q0. So we're gonna use P0, 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 Q0 in the next iterations still. Okay, all right, and then we're gonna use we definitely update the P1, Q1 as a P, comma Q. Now P is what? Actually P2, right? Q is what? F of P2, right? F of P2. Okay, all right. Let's see. So so what's the what? Now P1, Q1 just gone in the next iteration if f of what, f of P1, f of P2 times f of P1 is less than 0. Oops, what here? Okay, so this is a method of first position. So you need to fully understand the method first position, the algorithm first, okay, before writing code. Okay, so the this is the section, I mean the secant method and the method first position in section 2.3. So next time I'm going to cover section 2.4.